The absolute central engineering bottleneck of any scaling modern enterprise today is the massive legacy application monolith. These centralized, highly integrated systems hold extremely high business value, but they are crippled by rapidly accumulating technical debt. External demands like sudden data surges, shifting operational requirements, and continuous new feature requests hammer against this rigid structure, creating structural stress fractures across the application. A common executive misconception is that fixing this fragility requires a total rip-and-replace maneuver. Tearing down an established system to rebuild it from scratch is an extreme circumstance that carries a high risk of data loss and directly threatens core business continuity. System migration is always an exercise in carefully phased risk management, not a binary choice between staying broken or starting over. Architects have 7 distinct vectors of application modernization to choose from. The ultimate architectural goal is to use these vectors to transition from entangled monoliths to an automated ecosystem of independent microservices. Modernization is a spectrum of targeted architectural transformations. Organizations use this spectrum to systematically isolate and retire technical debt without causing operational downtime. This quadrant matrix maps out the primary architectural framework used to determine the correct migration pathway. We measure the level of code modification on the x-axis against the level of infrastructure shift on the y-axis. The initial prioritization phase requires architects to focus on high-value applications that carry the lowest amount of technical debt. The first pathway here is encapsulation. This leaves the original code and the host environment fully intact. Instead of rewriting, a protective API layer is built around the original code. This establishes new communication interfaces with modern external applications without risking internal system stability. Moving straight up the infrastructure axis brings us to pathways that require a moderate shift away from on-premise servers. Recasting takes existing application components and shifts them directly to cloud-based runtimes while preserving all original functionality. Replatforming sits right next to it. This optimizes the system for end-user performance while requiring only minimal changes to the original codebase. The key mechanism driving replatforming is app containerization. The application and its dependencies are packaged into a standardized container. This creates a lightweight, isolated runtime environment. Because it contains its own dependencies, it can be seamlessly deployed and scaled anywhere in the cloud. These first 3 methods extract business value and improve system response times, all while mitigating the risk of core code failure. When legacy code is too broken to simply wrap in an API or move to a cloud server, the focus shifts to the far right of the modification axis. This is refactoring. The current codebase is adapted and rewritten specifically to optimize back-end execution and resolve technical debt. The strict rule of refactoring is that the internal code logic changes, but the outside appearance and function of the program remain unchanged for the end user. Re-engineering abandons that restriction. It deploys fresh technology to re-architect the environment, actively enhancing productivity and generating new capabilities. Pushing to the absolute top right quadrant brings us to the maximum level of architectural intervention. Recreating rebuilds application components entirely from scratch. The original business scope is retained, but the architecture is new, allowing for the integration of customized advanced features. Restoration sits at the extreme edge. It is a last resort effort to overcome total systemic architectural collapse by engineering a ground-up replacement. As an enterprise moves further into this top right quadrant, the risk of operational downtime increases. Executing these vectors demands carefully phased rollouts and continuous application monitoring. Regardless of which of the 7 modernization vectors is applied to a given piece of code, the architectural end state remains identical. The monolithic system must be broken down into decoupled microservices. Monolithic systems operate on tangled, hidden assumptions, where one function quietly relies on another. Microservices force an explicit, boundary-driven system design. Because microservices isolate specific business functions, a component handling user authentication can fail entirely without crashing the separate component handling financial transactions. To manage this sprawling architecture of independent services, operations must adopt an everything-as-code methodology. This requires strict DevOps implementation. Infrastructure is managed, scaled, and repaired programmatically through code, rather than manual human intervention. Automating the infrastructure optimizes efficiency across engineering teams, embedding agility, resilience, and security directly into the deployment pipeline. Marrying the 7 modernization pathways with a microservice architecture replaces the brittle legacy monolith with a continuously deployable, highly agile ecosystem. The efficiency gains found in internal IT correlate directly with an organization's ability to exert economic impact in the broader market. The FarmScent case study illustrates this exact correlation perfectly within the $5.6 trillion global agricultural supply chain. The core operational bottleneck was that legacy supply chain software forces transactions through a fragmented, intermediary-heavy network. By utilizing modernized microservice architecture, FarmScent deployed a decentralized Web3 ecosystem. Structurally, this connected buyers directly to the farmers, permanently excising middleman margins from the data flow. Comparing the legacy baseline to the new architecture, the structural modernization resulted in a 300% profit margin lift for producers. Because the application was containerized, it easily scaled, onboarding over 200,000 verified nodes into the system. Processing this transaction volume and executing decentralized logic is mathematically impossible when trapped inside an obsolete legacy monolith. The prerequisite for any organization looking to scale is mapping their specific technical debt to the correct pathway on the modernization matrix, carefully selecting anywhere from encapsulation up to restoration. By maintaining an agile, phased migration, enterprises isolate failing code, retain complete control of data, and avoid operational downtime. Phased architectural modernization is the mechanism that allows a company to bypass traditional intermediaries. It is the strict prerequisite for deploying high-scale logic like AI and Web3.